Welcome to the flipped video on the electrochemical series, which is the new name that we're going to give the activity series. So the activity series is very similar to this series here. Remember, in previous videos you probably watched, we said that if you get metals and you put them in, let's say, copper sulfate solution, then some will react and some won't. And we noticed that there was a trend there that we saw that, let's say, magnesium reacted very, very rapidly. Then we saw that zinc reacted at a slower rate, copper was very, very slow, and silver didn't react that much at all. It was so slow, we said basically it didn't react. So we can see that there's a trend that as we go down in order here, their reactivity in copper sulfate decreases. And so when we did the same thing with acids, we also saw a similar trend, that if you place those same metals in acid, then you'll get different rates of reaction. Okay, magnesium very, very fast, zinc a little bit slower, copper not very much at all, etc. And so this series, which we called previously a metal activity series, we can write in a little bit more detail now because we understand about redox reactions, in the sense that we have equations here called half equations. And these ones here are called reduction equations. So this electrochemical series can sometimes be called a reduction series. So we start off with potassium up the top because potassium is very, very reactive. And potassium ion will accept an electron to form solid potassium. So this is the way it's normally written, a reduction equations, and shown in textbooks, etc. And they have numbers next to them, but we'll talk about that in another video. But if we just think of these here as the top is very, very reactive, and as you go down they become less reactive, and you can go lower than silver, you can go gold, and you can go platinum. Very, very unreactive there. Now when I first learnt this, I sort of flipped it around a little bit and wrote it the other direction, because it made more sense to my head, thinking that if you're very, very reactive, you want to get rid of your electrons and therefore become stable. And so therefore up the top you had metals that were so reactive they wanted to get rid of their electrons, and when they become oxidized they're causing other species to become reduced. So that's why up here we're saying up here is strong reductants. Remember, a reductant is a chemical that itself is oxidized and loses electrons and forces another chemical species to be reduced. And so I wrote it around the other way. And in a lot of textbooks you can see it this way. Same sort of thing happens as long as you work it out in your head. So up the top we've got strong reductants. Down the bottom we've got very weak reductants. On the other side of the coin we could say these are strong oxidants. So in other words, copper is a very strong oxidant. Now remember, an oxidant is a chemical that itself is reduced and causes another chemical species to be oxidized. So depending upon how you think about it. Now what's the use of this table, I hear you ask? Well, I'm glad you asked me, because I'm about to tell you. This allows us to determine the spontaneity of metal displacement reactions. So in other words, do the reactions occur spontaneously, or do they not occur at all? Well, let's look at some familiar examples that we've looked at before. So if we have a beaker, and in that beaker we put our strip of zinc. So here we have a zinc strip, and in here we place some copper sulfate solution, so I'm just going to write the copper ion there. Is a reaction going to happen there? Is a metal single displacement reaction going to happen? That is a redox reaction. Well, let's have a look. Here's zinc, and zinc is higher in the series than copper. So here is the rule. A reaction will be spontaneous if the reductant is higher than the oxidant. And so here's the oxidant, here's the reductant. So the metal is higher than the ion here. So a spontaneous So when the reductant is higher than the oxidant, I like to think of it like this. Here we have zinc. Is it possible for zinc to lose electrons? Yes, it is. And so is zinc higher than copper? Let's have a look. Yes, zinc is higher than copper. So it has a possibility of losing electrons. Can copper lose electrons? No. It can gain electrons. And so if this is higher than that, and this is going to lose electrons, then this is going to pick them up. So this is going to be the reducing agent. This is going to be the oxidant, right? And so therefore we would say, okay, yes, it will be spontaneous because zinc is higher in the series. It's more active. It's going to lose its 2 electrons, okay? And it's going to give those electrons to copper. So remember, this is called a reductant. It causes copper to be reduced. And copper is going to be reduced to form metallic copper on the outside, and that's what we're used to seeing. So in that example there, it's a spontaneous reaction because the reductant is higher than the oxidant. And another way of thinking, which my brain prefers, is zinc is higher. Zinc can lose electrons than the copper. Let's consider a situation which may not form a spontaneous reaction. So let's rub this out. Okay. So in this instance here, we've got some zinc sulfate and a copper strip. Is this going to have a spontaneous reaction or not? Well, let's check it out. Let's go to the table. Here we have copper. And we've got zinc. Now, zinc is higher than copper, so zinc's more reactive, so you wouldn't expect that this is going to happen here. So at the moment, can zinc lose electrons? No, it can't. Can copper? Yes, it can, but copper's not going to because copper is lower than the zinc half equation. So we're going to get no reaction. Okay? Copper is not more reactive than zinc, and therefore, even though it can lose electrons, it's not going to because it's lower in the series than zinc. Okay? So that's an example of a reaction which is non-spontaneous. Hope that makes sense on how to work out the spontaneity of a chemical reaction, a displacement reaction. And this is going to become important because we're going to think, what combination of metals can we use to make batteries? This is where this is leading. If we can work out combinations of metals that are far apart and one wants to lose electrons a lot and the other one wants to gain them, we can make that reaction happen and put that into an external circuit and make a battery. More about that later, but that's the link for where we're going. Okay? I hope that makes sense. See you in the next video.